So what I'll do through this lecture is basically introduce you to all the basic concepts of population ecology. These are common to whatever species you're studying. And then after that, we'll go through some bird-specific examples. Also inherently population ecology is quite mathematical. So we'll also go through some basic equations. Essentially, the idea is that you guys should be aware of when you read papers involving populations, you should be able to understand what those terms mean, right? So we'll go through some of the basic terms. First of all, what is a population? So, from this definition, can you tell me what are the key terms that we should be looking for when defining population? Yeah, that is one thing. So, individuals of same species that interbreed. What is the second important thing?
Same region and the same.
Yeah, so there is space. So there is a group of individuals which interbreed, which obviously belong to the same species accordingly. Then there is the concept of all of them being sharing the same space and occurring at a point in time. Okay, so these are the three important things that describe a population. Sum of individuals interbreed in the same region and at one point in time. So these are some key jargon when it comes to population ecology. So them occurring in the same region, you refer to it as geographic closure. Then, because we are referring to a point in time, that is referred to as temporal closure. Okay, so I'll explain these terms better in the coming slides. And often population is expressed in terms of density. What it refers to is basically the number of individuals belonging to a species, that is the population number, divided by a certain area. So basically, when you talk about density, you are referring to population in terms of a certain area. Okay, so you divide it by the area. So that okay. And also, as I already told you, population refers to one point in time, right? It's a snapshot. But over time, you don't expect it to remain static. So from time t to time t plus 1, most often you'll expect the population to change. Okay? So now we look at what processes cause a population to change. So when we are talking about the difference in population size, when we move from time t to t plus 1, which is the next time interval that we are looking at, and you look at that difference, there are some processes which make this change happen. And there are four basic processes that cause these changes. First of which are births, right? Births add to the population. Then there is immigration, which is addition of individuals coming from outside the area that you are interested in. Then there are deaths, right? And then there is emigration, right? So these are the four processes. Often this is called the BIDE model, BIDE, right? So these are the four processes which cause changes in a population over time. So if you look at it, births and immigration are the two processes that add individuals to the population, right? And death and immigration remove individuals from the population. Okay, so they cause negative changes. And another way of looking at it is also that births and deaths are internal properties of that population that you're interested in, right? That happens within the population, whereas immigration and emigration are with reference to other populations with which the population that you are interested in is interacting, right? So those are external factors. So as I already told you, this is called the BIDE model. As you can see, if you have to get at the population size at time t plus 1, it is the initial population size at time t. Then you have all the population members that are added because of birth and immigration, and then you subtract the number of deaths and emigration. So this gives you the population at the subsequent time step. Is this clear? Yes. To everyone? Yeah? Okay. Now we'll look at somewhat simple equations. So we just saw that particular equation, and let's just ignore migration. So we are going to ignore immigration and emigration. Just think of it as an island population where these two factors don't matter. So now we have only births and deaths. So now the equation becomes NP plus B minus D. So B is adding individuals, death is removing individuals, right? And let's express the number of births per capita, that is number of births happening in the population divided by the total population size. Let it be small b. Similarly, number of deaths per capita, let's express that as small d. So we have two more terms, b and d, small b and small d. So here again, the same equation can be rewritten like this, right? B, capital B becomes small b into n, and similarly capital D becomes small d into n. And again we divide the whole equation by n. So now we have nt, which is the second population size, divided by the initial population size, that is now 1 plus b minus d. And this is often expressed as lambda, and this whole thing is called finite population growth rate. Okay, so basically you are expressing the it's like a change, right, from the change from the initial population size to the next population size, and that is expressed in terms of this equation, and it is referred to as lambda. Okay, now let's get back to that equation again. And if we subtract nt from both sides of the equation, so here basically what we have is nt minus 1 minus nt, and again from here also we removed nt. So then what we get is delta n, which is change in population size, right? First we looked at the ratio between the second population size and the first population size. Now we are looking at the change, the magnitude of change between these two times. And so what we get is the rate of change, okay, the measure in population over a small time interval. So we get a differential equation, dn by dt, right, is equal to bn minus dn. And then what you do is you normalize it by the initial population size, so dn by dt divided by n, and so what you get is birth minus deaths. So that is your intrinsic rate of change for a population. So it basically describes just the number of additions that happen in a population over time. Right? Is it clear for everyone? Are we all on the same page?
Yes.
These are very, very simple equations, and population ecology is extremely mathematical. So these are the simplest terms that we should be aware of, and both lambda and the R, the intrinsic rate of change, you will find them in many, many papers dealing with bird populations. So it's important that you are clear about what they mean, right? So if you look at it, this is how they look like when you plot them against time. Okay? So the lambda is basically a discrete quantity. So it will look like this. Whereas the way R is derived, it's a continuous value, and this is the relationship between lambda and R. Okay? Fine. So let's look at how these values are used while managing bird populations. Okay? What do they mean when it comes to managing bird populations? Those are the equations. So you can just imagine here, when the population is increasing, we'll assume that the B is greater than D, births are more than deaths. In that case, just fill the values in look at those equations. So what will happen is R will be greater than 0 and lambda is going to be greater than 1. Is it clear from the equation? So when we want to infer that population is increasing, these are how these values have. This is how they are supposed to be. Okay? When the population is stable, births and deaths are going to be basically equal in number. So R is going to be 0 and lambda is going to be 1. And when population is decreasing, similarly, R is going to be less than 0 and lambda is going to be less than 1. Yeah? So now when you read bird papers, or especially conservation papers which report these values. I hope you can understand them, keeping this in mind, better. Okay. Two other parameters that we see very often in many bird studies. Yesterday I talked about it as well when I was talking about life histories. Is annual survival, right? I kept talking about annual adult survival and all that. So what that refers to is basically proportion of individuals surviving between time t and time t plus 1. Okay. So what this means is basically you have the population size at time t plus 1, and you have to subtract the contribution by birth and immigration. Okay, those are the ones that are added to the population subsequently. What you are interested in knowing is that from the initial population, how many have made it to the next time step. Okay, you are not interested in the addition because of birth and death. Okay, and you also standardize it by the initial population size, right? Subsequently, recruitment is another term. Recruitment exactly refers to what we are not interested in here. So recruitment is basically the number of individuals that are added from time t to t plus 1. That is the number of individuals that is contributed by births and migration. Okay? So is this clear for everyone? These are the terms we looked at in all those equations. You have population size, the density, then you have proportion of, we didn't look at that. I'm sorry. Ignore that. Then we looked at the births and deaths per capita. Then we looked at survival, right? Recruitment rate, finite population growth rate, and intrinsic rate of change, right? R. So of these, the first three terms, or first two terms in our case, are known as state variables, okay? And the rest of them are known as vital rates, okay? State variables are all these terms basically are usually based on one-time sampling, and they give you some information about the current state of a population. It doesn't tell you anything about whether it's growing, whether it's declining, or anything. It's just like all these terms give you some sort of snapshot about a population, right? Whereas the vital rates are derived from usually multiple years of data. So you monitor a population over many years, and then you try to understand how that population is changing, right? So in most conservation studies, if you want to look at impact of some sort of habitat change or any perturbation in the environment, there are two ways of looking at it. One thing is that you can look at a gradient of that disturbance. So for example, forest fragmentation. If you want to look at the impact of forest fragmentation on a bird population, there are two ways of looking at it. One way is you find a lot of fragments of different sizes, right? Start from an intact forest, which is really huge and meets the requirements of the species. Then you go down in terms of the size of fragments, and then you can measure density or abundance across that gradient, and then you can make some conclusion about how size of fragment matters to a species. The other way of looking at it is like you study the same population in one place, and then you see the changes happening to that particular population over time. Okay, so depending on your question, you might want to look at state variables or vital rates. But most often, because in terms of conservation and all, we are interested in looking at how the population is doing over time. So if the data we should always be trying to get at vital rates. And there are some other factors which we are not covering during this course, which also make state like the first density and abundances not very good at conveying how the population is doing in some instances. So the endeavor should always be to get at this, but because it's very time consuming, takes a lot of time and effort to put in, it's not easy to do, and particularly in our country, we don't have this kind of data for most species. There is one major gap in when we study bird populations, particularly in India. Okay. So I'm just going to go through some example examples from different countries where people have looked at these parameters and have tried to understand some ecological processes. For example, there was a study which looked at the density of mating pairs in protected areas in Finland in two time slices between 1980 to 1999 and 2000 to 2009. And here they were interested in looking at how change in climate has influenced density of mating pairs within their protected areas. So basically, the protected areas, other than the impacts of climate change haven't changed much, right? The influence of other disturbances has been minimal because they are only looking at protected areas. But over this time period, the climate has obviously changed considerably. And what they find is that in the northern protected areas, the decline in densities is much starker as compared to southern and across the whole country. Yeah. Then this is very interesting study which looked at population survival, and they looked at the impact of West Nile virus. So this is a disease which it's a virus which impacts bird population, and this spread across North America between 1999 to 2003. And what they found is 42% of the species, they suffered declines at the continental scale. So millions of birds died because of this particular disease. But when they looked at the impact of this virus on different bird species, they found that there was a very differential response to this particular virus. So if you look at these two species, when they were first exposed to the West Nile virus, their annual survival declined, right? And subsequently, as the exposure to the virus remained, they kept declining, right? So once they were exposed, they started declining and they continued declining. But there were some other species which declined in terms of their annual survival when they were exposed to the virus. But after that, they recovered, although they have evidence to show that the virus was still there in the environment. Okay, so they found that there's some sort of phylogenetic influence on how the species are responding to the West Nile virus. So there were some groups of birds which seem to be able to recover after impact, some birds which are not able to recover after they are impacted. Yeah. Okay, this is another interesting study which was recently published where they looked at this particular species, Carolina chickadees, and what they found was in their habitat, as the proportion of non-native plants increased, so basically invasives and other exotic plants, the proportion increases. You can see, so this is the level at which the growth rate is equivalent, is enough to replace the population. So basically, the number of birds and deaths is equal. But as you see, as the proportion of non-native plants increased in their habitat, the growth rate kept declining. Right? So this is some way of using it. Now I'll just show you an Indian example. So this is the white round vulture. This is one of the few species in our country which has been monitored over a very long time period. So the Bombay Natural History Society started monitoring this species once it started declining. I think it started in 1991, and from then, every 2 years, they have been monitoring these road transects which are distributed in eastern India, western India, central India, and northern India. And what they do is they count the number of vultures that they see from as they're driving in a vehicle. So, but even for that species for which we have so much data, we don't have any robust population estimates. Like we don't have any idea about what their actual densities are. We don't know about survival rates. We don't know about recruitment rates or any of the population parameters that I talked about. Here, in this case, what they use is a very crude index. So that's the best we have for any species in our country over a long period of time. Okay, so this is one area that needs a lot of work. Okay. So another important thing to look at when we talk about populations is that we talked about densities, and densities are not uniform everywhere because populations are not distributed in space similarly everywhere. Essentially, the way individuals of a population distribute themselves is in response to some resource, and depending on how that resource is distributed, the populations also tend to be dispersed in different ways. So, for example, they can be clumped, like you see it in case of many flocking birds, right? Where, say, frugivores or something, where the resources themselves are clumped in the environment. So, accordingly, for those birds also, their distribution is clumped, right? When resources are more uniformly distributed, you see, accordingly, the individuals also disperse themselves more uniformly in space, and this is seen in the case of many territorial species, right? And of course, if the resources, if there is no relationship between them, or you also see random distribution, but that is pretty rare to come across. Okay. Now we'll look at population growth rates. So there are two ideal models that are often used to describe two kinds of population growth. One is called exponential growth, and the second one is called logistic growth. So first we'll look at the exponential growth. So in this case, what we see is that the population grows exponentially, and after attaining the peak value, sometimes the population may abruptly crash if there are not enough resources in the environment. And so basically this is what happens. This increase is continued until the individuals consume all the resources that are available in their habitat. And this growth rate, dn by dt, is basically expressed as r into n. You remember the equation for r? It was dn by dt divided by n. So it's basically the same thing, the rate of change. So this growth rate is only determined by the intrinsic rate of change of the population, just r. So it just keeps increasing accordingly based on the value of r. And one of the examples that we see amongst birds is the example of whooping crane. This bird practically went extinct. I think it reduced to about 40 individuals in the 1940s, mostly because of hunting. And thereafter, some conservation efforts came into being to recover the species, and this is the way it grew. So by 2005, there were about 340 adults in the wild. So because obviously it was not, their population didn't decline because of lack of resources, right? There was abundant amount of resources available in the environment, and so when the pressure due to hunting was removed, the way they grew, basically it represents an exponential growth pattern. The other extreme is logistic growth rate. So this happens in most cases where the environment has some sort of carrying capacity in terms of how many individuals it can support. So when we look at logistic growth, there are distinct phases. So when initially a few individuals come into an environment or a habitat, just because of the number of individuals that it starts with, the growth rate is very slow, and this is known as the lag phase or positive acceleration phase. Then in the middle phase, the population starts increasing very rapidly, and so it's called the logarithmic phase, right? And towards the end, as it reaches carrying capacity, it starts slowing down. That is known as the negative acceleration phase. So when you look at the equation, it's very similar to the first one, but there's an additional term. So you have dn by dt is equal to rn, and this is multiplied by this term 1 minus n divided by k. So basically this term 1 minus n divided by k is known as the environmental resistance. Okay, so basically because the amount of resources available in the habitat kind of puts a cap on the number of individuals that habitat can support. So as it starts reaching their carrying capacity, it starts resisting the growth that is happening. Okay, so it slows down, and accordingly that's the equation. Yeah, and most often you see that this kind of growth rate for most large mammals, and yeah, any species where carrying capacity determines matters, you see logistic growth. Now, when it comes to regulation of population growth, there are two types of factors which determine how the population grows. The first of which is density dependent factors. So these are the factors which influence birth and death rate as a function of density, right? And so basically, most commonly it is manifested in terms of area-specific competition. So basically, individuals within the same population are competing with each other for resources. So as the population size increases, this competition will also intensify, and accordingly, the growth rate will decline in proportion to the intensity of competition. So basically, because of competition increasing, it will push down the growth rate as the density of individuals within that patch increases. And we see this in nature. So like for example, for great tits, we see that as the number of mating pairs increases, the average clutch size goes down. Okay? Other than that, there are some other factors which influence growth rate which have not got anything to do with density. So in this case, the births or deaths are not a function of density. It's because of some other factors. Most often these are abiotic factors, so like things like fires, floods, or some extremely harsh weather. In this case, you can see a song sparrow population, and the population of the females nesting on a particular island in British Columbia, and they find that it is periodically reduced by a very severe winter. Okay, so that has got nothing to do with the density of population, but it's just that harsh winters causes greater mortality. Okay, so these are called as, these are known as density independent factors. Then in nature, when you look at birds, you see all these different kinds of growth patterns. So that is a red grouse, which shows some sort of cyclical growth pattern. Then you have late European shags, which seem to have increased following an exponential growth pattern. Similarly, so you see all kinds of different growth patterns. Often what we see is these cyclical growth patterns. Basically, these are like periodic phases of high growth rates or booms, and then again they following that they just collapse, and then again after some time they experience this cycle over and over again. So one of the examples are these crossbills. So they basically track the spruce crop. So they feed, crossbills feed on cones, right? They have a very special beak adaptation to pry open cones and feed on them. So they depend on this spruce crop, and because the spruce crop goes through these cycles, they basically track the spruce crop in their population growth as well. Yeah. A similar cyclical pattern is also seen in these yellow ptarmigans. Interestingly, they follow a 10-year cycle in British Columbia and Canada, and the same species in the UK follows a 4 to 5 year old cycle. So it's not very clear why that happens. But it must be because of them responding to different kind of resources.